Hello everyone, welcome to the course. So in this course entitled Material Science for Nuclear Energy Applications, my name is Karim Ahmed. I'm an associate professor here at Texas A&M University. And in this course, we will cover the basics and the fundamentals of material science and their utilization in nuclear energy systems in general. So in this specific lecture, I will go over basically an introduction to the importance of materials in general for all engineering applications. And then during the next lecture, we will talk specifically about nuclear energy applications. However, while this course is geared towards nuclear engineers and it focuses on nuclear or the application of material science in nuclear energy systems, most of the materials that we cover, like I would say 85% to almost 90% of the materials that we cover during the course would be basically applicable to any engineering or science field that is basically will have one or will have course like that as basically introductory material science course in those specific disciplines or majors. So having said that, let's go ahead and introduce the course. So again, this is the first lecture. So this is just a generic introduction to material science for engineering applications in general, really. So of course, one important first question that we should think about and we have to answer first is why study materials? And of course, for maybe even immediately, that basically for most engineers, that seems like a very clear and obvious, or there are several very clear and obvious answer for this question, but what's immediately clear is, of course, materials are important. So there are a few important reasons. First, of course, everything is made of something, right? Basically, it's a materialistic world, whether we like it or not. And we cannot really, as engineer, to make devices and components, we have to basically pick materials to make those or manufacture those equipments and devices from. And basically also, of course, in that regard or in that sense, materials will enable or limit new technologies. So whether we talk about aerospace applications, we talk about biomedical engineering applications, or in our case, nuclear energy applications, so advanced reactors, fusion reactors, and even with everyday materials that we use, something like with portable or even wearable electronics, all of those are examples where basically those are advanced applications, and for advanced applications, you need materials or advanced materials. Also, basically, as engineers, we also care about the performance and the safety of those devices and equipment. So basically, we need to be able to predict the material behavior under specific operating conditions. And that's definitely for something like, in our case, nuclear energy and aerospace applications and other structure engineering application. That's of course very important because that's a main concern in regard of the safety. Um, so those are, of course, clear examples of why we care about materials as engineer in general. And now if we focus on, in our case, as nuclear engineers, of course, it's very clear. And one interesting fact to notice here is that in many reactors, we are many of the basically advanced or basically even current reactors are usually named after materials that are used in those reactors. So light water reactors, heavy water reactors, sodium cooled fast reactors, lead cooled fast reactors, gas cooled reactors, and molten salt reactors, and so on and so forth. Almost every reactor we know is basically named after a material that we use in that reactor that enable specific performance or a specific safety mechanism that would be particular to that reactor type. And again, to expand a little bit on that, actually, as part of the licensing process, so the NRC would actually look into the material qualification as part of the licensing process. So basically, you have to show and demonstrate that basically there are standards in terms of the manufacturing of the materials that you are following, and also that there is enough test has been done and there has been enough documentation of material properties, data sheet, and things like that to basically make sure that these materials will, of course, withstand the service or the operating conditions in nuclear reactors. Especially in our case, we require materials to basically in traditional reactors to stay or serve for decades. Those most current water reactors serve for at least 40 years, and then you can even expand that now to 80 years and maybe even more in the future. And of course, one of the known code qualification for materials is basically the American Society of Mechanical Engineer, or ASME. And while that materials that are already qualified in ASME would basically kind of succeed or already proceed as a first step in something like NRC qualification, but however, that's not enough for nuclear energy applications. So things like basically the environmental effects, right? Depending on the environment that the reactor, the operating condition of the reactor, whether those gas-cooled reactor or molten salt reactors, it will be combination of environmental effects and also radiation effects. So there have to be specialized testing and documentation of the material behavior under those conditions, and sometimes also under the coupled or synergetic effects. So for that reason, it is very important to note that basically the qualification for materials in nuclear is basically have very high standards and basically could take more time than any in any other applications. And this is of course part where now advanced modeling and simulation and AI is basically projecting and currently actually accelerating this process. And we're going to talk about that as we go on in this course. All right. So basically, the outline of this lecture is to talk or to introduce the material science and engineering field to you and to discuss and give examples on the importance of the utilization of this field in different engineering and science disciplines and applications, and also to talk about a little bit of the fundamentals and basics where basically we connect the materials and their composition and their structures to their properties. Again, this is the first introductory lecture, and then in the second introductory lecture, we will uh, shift the focus or gear the talk more toward specific applications and specific fundamentals related to nuclear materials and nuclear engineering. All right, so what do we mean by material science and engineering as a independent field? So the first thing to note is basically the fact that it is not really a new kind of uh, branch of science to some extent, but it is basically rooted in physics and chemistry. And if you are studying biomedical engineering and biomedical materials in general, that would have some also roots in biology. So its roots is basically in the basic and fundamental science and scientific fields. However, it branches to all applications, mainly all engineering applications. So, of course, when we talk about structural engineering, civil engineering, aerospace engineering, and nuclear energy or engineering, all of those engineering disciplines or fields will utilize material science and engineering as basically the main connection between the fundamentals of physics and chemistry and biology and the application in engineering. So there are two ways to study and learn this scientific field, which is basically to talk about it from the top bottom approach or the top or the bottom top approach. So we can start from the atomistic scale, right? Basically an atom's first approach and look at how the composition of the material would affect its structure, and that could be initially from the crystal structure all the way to the micron scale structure, and then eventually to basically the device or the equipment that we have in mind, and we will see that basically the performance of the equipment or the tool at the end of the day is related to all those different scales that we looked at, from the atomistic scale all the way to, let's say, the millimeter or centimeter scale that we can see by the naked eye. And that would be mainly kind of like the science or what a material scientist would do. It's basically the scientific way of trying to understand as much as we can. However, in some cases, when we talk about engineering, it is usually we have a specific application or device in mind and we want to improve its performance or lower its cost. So we can look at this basically process in reverse, and we look at how to improve its properties. So we get which which basically mean we are trying to optimize its performance, so we improve its properties. And to do that, we can look back at what should be the microstructure look like, and then we can even zoom in further and we can look at what should be the atomistic structure and the composition on the atomic scale should be like. And as we will discuss in a few minutes, basically the connection between them would be during the manufacturing. So we can also look at which type of manufacturing methods that we can use or select to be able to basically uh, induce or form such microstructure. So again, this is of course, relatively difficult task because the material is inherently, or any piece of material is inherently multi-scale in terms of trying to understand its either properties or its behavior. So basically, that's of course can easily understood if we imagine how many atoms, if we try to count or basically have an estimate of how many atoms we have in any piece of material. So if we even look at 1 millimeter cube of any solid materials, we will have at least Avogadro's number of atoms. So we cannot really track those atoms or try to understand the properties and the change of their properties or the change of their response to any outer um, operation condition based on basically tracking all the atoms in the system. So we use basically the traditional concept of divide and conquer, where basically we can look at different scales and then try to understand the behavior, the property, and the phenomena that's happening in those scales, and then we connect those scales together. And we can now, with advancement on both sides of the world, whether it's modeling and simulation or experiments, we can do that actually hand in hand in the sense that we can look at those different scales using different types of models and simulations, or using different characterization techniques and tools. So this is one of the most important um, takeaway message, not just of this lecture, but of this entire course, which is basically what is the ultimate goal of material science and engineering as a field. And this is basically to connect those what we call the four pillars of material science and engineering, which are the processing, how we make the material, and then the structure based on that, how does it look like when we characterize it, and then the properties for that structure, what is basically the emergent or the emerging properties of that structure. And of course, based on the properties that lead to specific performance. So those four pillars are connected. And again, if we look at them from the uh, top bottom here on that slide, that's basically the scientific way of looking at things, right? From the structure all the way to the properties and performance. And again, those are connected, of course, the relationship, if we understand this relationship fully or completely, then we can basically also look at it from we can basically reverse engineer that and look at it in the opposite direction or in the reverse direction. So we can optimize the performance by basically looking back at how those things are, sorry about that, how those things are related. But again, keep in mind during the entire course that this is basically the ultimate goal. This is basically the holy grail of material science and engineering. So it's basically trying to establish relationships between the processing, structure, properties, and performance. All right, so a little bit about the historical development of materials over the centuries here, and that's again speak to the importance of materials, is there are several periods or ages during human evolution where we basically named them after materials, like when we started with the Stone Age, Bronze Age, and Iron Age. Interestingly, however, in the first like 15 or 16 centuries or so, we didn't really try to make a lot of man-made materials. We worked with what's already in nature, so basically naturally occurring materials. So there was, of course, lack of advancement in chemistry and materials compared to something like physics, where basically physics started to really take off in the 17th centuries or even in the 16th centuries. It's not until before, sorry about that. Let's go back to that slide. So it's not until basically, sorry, not really until the Industrial Revolution, where we started basically having some tools that we can use to start separating the materials. So a lot of the naturally occurring materials are minerals and compounds, and especially with metallic-based materials are usually oxidized. So it was difficult initially to separate those components and basically retrieve the elemental versions of those materials. It's really until we have tools at our disposal like thermoelectricity, basically to thermoelectrical tools and also basically polymer science and all of those things in order to be able to actually separate those materials. And then after that, we were able to kind of basically mix and match, and that's where material science really started. And we're gonna talk about that next. So it's basically, so I think my notes. Oops, okay. All right, so that's basically again back to that evolution during different centuries. So of course, as you can see during really the starting from the 19th centuries where we started actually making a lot of new man-made materials. And again, that's for the advancement of thermochemistry and because of the advancement in thermochemistry and electrochemistry. And by now, we actually have more than 180,000 materials. So it's about just shy of 200,000, what we would call basically engineering materials. So this is not all the materials that have basically been synthesized or man-made. Actual number will be much higher. So if we count organic materials and pharmaceutical materials, that would be in millions. But what we can think of as engineering materials that has some useful engineering application, those are more or less close to about 200,000. Still, of course, it's a very huge number, and that's also, again, an important goal of material science and engineering, and something that engineers have to learn is basically how to select the right material for the application in mind, because technically we have a lot of options. Although, as we're gonna see and discuss later, those options shrink very rapidly in extreme environments. So why do we have such large number of materials? Although you can ask, we only have about, let's say, 90 elements on the periodic table that are basically not gases or radioactive, so useful for engineering applications. And that's because of the fact that we can mix and match. So basically we can have materials that are formed or consisting of several elements. Most alloys, for example, like with steels and nickel-based alloys and aluminum-based alloys, those will have around something between 8 to 10 components. Yes, usually there are 3 or 4 main components, but still overall most advanced alloys will have something like uh, 10 or more components. And then you can basically get an estimate of this huge or large combinatorial number by basically estimating if I have to pick 2 or 3 elements out of 90, then how many options do I have? So this is a simple combinatorial calculation. So for binary systems, this turn out to be in about 4,000. You can see the interesting trend is that as you increase the number of elements that you are going to accommodate in this material, the candidates or the total uh, number of options increase very rapidly. So if you just have an alloy that's consisting of 4 elements, you have more than 2.5 million candidates. And that's why we have, of course, a lot of databases to try to document some of those materials when we either predict their properties or when we actually make them. And as we're gonna discuss also in a few minutes, that's of course one thing that now the advancement in modeling and simulation and AI is basically taking this to the next level because, of course, initially you don't know which of those options and candidates will have good material properties. So up till the last century, that was almost kind of like by trial and error, which of course very ineffective. Right now, we can accelerate this process a lot by basically trying to predict the properties. The other tool at our disposal that we can use to also make different materials is basically the microstructure. And that could be at different scales. So even a specific material like carbon, which is of course one of the most fascinating elements, could even have different crystal structures, so different phases. We're going to talk about that in this course. Sorry about that. So even for the same element, so even if we're talking about specific element, it could have different crystal structure at different temperatures and pressures. That's a phenomenon that's called allotropy that we're going to talk about. And also, we can basically make composites or change the microstructure of a specific element at different scales. So when we make carbon fibers or carbon-carbon composite, still, again, we're talking about the same element, but we can prepare it in different ways. So again, this is another attribute in addition to the composition that we can mix and match different elements. Even if we just use one element, or even if we use just two or three elements together, we can u- change the microstructure, and that also could change their properties and therefore their utilization in different applications. So in summary, basically we can say that there is difference between matter and materials, where matter here we're talking really about specific elements, and those are governed by their equilibrium structure or atomistic structure, which basically we're going to talk about later. But basically, there is most stable configuration is the configuration with the lowest energy, and that's more or less fixed for each, at least for elements. However, we have a lot of options at our disposal to change their properties and make material out of just basic or fundamental elements that we see on the periodic table, and that's by combining different elements or by inducing different microstructure in those elements and their compounds. And that's usually using different manufacturing techniques. So back to what I was saying earlier. So basically, while we have about 200,000 engineering materials, we can see that basically this number shrink very rapidly when we talk about really harsh or extreme conditions like what we see in aerospace application and nuclear energy applications and things like that. So basically, if we have extreme temperature, right, or very high pressure or radiation effects, like in our case, or corrosion, those are aqueous corrosion or basically molten salt corrosions. We see that based on, or in case of extreme environment, then those options usually basically are limited, and we really have a handful of materials. So one a classical or traditional example is for high temperature materials. So if you are looking for temperatures that can serve at around 1,000 Celsius, so we'll basically have a few kind of subclass of materials, or subcategory of materials. So we have basically some technical ceramics like carbides and nitrides, because those have very high melting point. Same with refractory metals like basically tungsten and niobium and their alloys. Also a little bit of oxide and silicide. So again, technical or advanced technical ceramics. And That's because those materials have very high melting point. However, the melting point might not be even the limiting or deciding factor, because as we will discuss in this uh, course later, basically if those materials are under or serving under stresses, or if there are other environmental effects like irradiation or corrosion, the material could still fail mechanically or structurally even before basically reaching high temperature. So basically, eh, the strength of the material, so that's basically a phenomenon that's called the creep that we're going to talk about later when we talk about the mechanical properties of materials. So the creep strength of almost all materials will reduce as we increase the temperature, because the creep phenomena happen at basically relatively high temperature, where basically the temperature is close to 40 or 50% of the melting point. While the creep strength is basically how the material will behave under constant static load, and that will reduce a lot at high temperature. So in this bubble chart of materials, we can see the strengths at around 1000 Celsius. We see that basically if we try to find an option where the strength is above 100 megapascal, which is basically in many applications, that would be really the bare minimum. So anything above this line is basically our only option for materials to have relatively high creep strengths at relatively high temperature. Again, you can see some of what we call the super alloys and technical ceramics and refractory metals. However, you can see if we are trying to optimize against other important deciding factor, like for instance, the density of the material, so how heavy the material is. And of course, you can see that this would be important for aerospace applications. So you can see, unfortunately, many of those options would basically not necessarily satisfy both criteria or both conditions. So it is also important to keep in mind that in many cases, when you try to select specific material, you will need to basically have or make some trade-off, and also to base your selection on the combination of different properties of materials. But the main point is basically we are going to see this trend as we continue in this course when we look at different applications, which is basically, although in theory we have a large number of engineering materials to select and pick from, but when we actually talk about very advanced applications and materials serving at challenging conditions, that basically we see that we always end up having just basically handful of materials that can serve in those conditions. And that's also the motivation, and that's why this field of material science and engineering is rapidly growing, because basically, of course, we need to come up with or explore new materials and new manufacturing methods to be able to exponentially increase this number of materials, because based on the combinatorial numbers that we looked at before, in theory, the number of materials that we can make is basically infinitely large. Another important thing to keep in mind is now when we select materials also, in addition to, of course, their properties, we have to keep in mind also the eco design and sustainability. So basically, you have to see how the manufacturing methods that we are using to make those materials, how they are going to affect the environment. And this is, of course, for the welfare of our society. So we need to look at, or we need also to take into account those those factors while we are selecting this material. So a few of those important factors is to look at basically how much energy we need to make this material, right? So that's of course an important factor because it always goes hand in hand with basically the amount of coolant that you need or the cooling power. So basically this is all are related, and also the carbon footprint. Of course, depending on the energy source, if something like renewable energy and nuclear energy, then the footprint would be much lower. But those kind of three environmental factors or environmental effect of making the material are relatively proportional to each other and goes hand in hand with each other. And also that explain why it is very important as we advance our society and our ways of making materials and adding new materials, we have to always try to use basically green energy source to reduce the footprint of carbon dioxide. And we can see also different types of materials and how they stack against each other in terms of those environmental factors. So we can see most of the advanced materials and even the commonly used materials are actually high in that regard, in the sense that basically so the advanced alloys, advanced technical ceramics, and even some of the polymers and plastics and carbon fiber reinforced plastics like here, those all takes a lot of energy to make, and that will again go hand in hand with the carbon footprint because unfortunately we're still not using enough of green energy sources as we should be. And of course, also one important parameter or factor to think about is the recycle fraction or recyclability of those materials. And you can see that basically while some metallic components and metallic alloys have high fraction, many polymers and plastic will have basically a very low fraction, and we're gonna discuss the reason for that. That has to do with basically the structure and the way the material degrade. Same with fuel, so we basically, of course, utilize a lot of different types of fuels. But in general, if we try to rank all materials, including fuels, together to basically try to just have an estimate of how much or basically how many tons of materials we are producing, we are producing something in the basically very in the 10 to power 10 or 11 here tons per year of different materials, mainly for fuels, of course, are the highest. And then steels and concrete would be also very high. So about that. Let's go back. Yes. So of course, concrete and steel, that would be like if we try to guess which materials we are producing the most, concrete and steel will definitely be our candidates, just because how versatile they are and how many applications we are using them. It's basically the really the bread and butter of infrastructure and advanced society. However, also now in terms of course of plastic, which is another issue, but also we are producing a lot of different kind of polymers in general and especially plastics. And actually, if we rank those materials by volume, because of course there's a large difference in density, well, actually the plastics could be a basically at much higher place in that ranking. So as just basically a figure or an estimate of what we look of what we looked at in that figure, we are producing about 10 billion tons of engineering materials, which consume about 16% of global energy. And of course, steel and concrete are basically leading the way because of their versatility and the many applications that we are utilizing them in. Then in terms of fuels, of course, we saw that oil and coal are basically we are using are the most produced and still most used fuels. And because they are very inefficient, we need basically billions of tons of those fuels. However, if we look at the uranium production, for example, and again, actually, nuclear energy, while still, of course, not high enough as a fraction of producing energy worldwide, but still it produces about 10%. So that's still a reasonably important fraction. However, we only need about a, a few um, tens of thousands of uranium, but that's because, of course, nuclear energy is very efficient, and that's what we're going to talk about in the next lecture. But for that reason, we can basically produce a lot of energy while consuming much less fuel than traditional um, energy sources. The other important thing to know about materials and their application is, of course, materials, we use them also in many medical applications and biomedical applications. It really saves lives. So we can use them as transplants and implants for or in different parts of the human body. We also in general, of course, our cells, so as humans, on the fundamental levels, our body is controlled by how our cells behave. But at the end of the day, our cells are made of molecules and atoms. So basically, of course, we are still consisting, or we do consist of materials like anything else. By weight, we are mainly oxygen. That's of course because water. So by mass would be oxygen. By not by just sheer number of atoms would be hydrogen. And basically humans would have uh, about 10 to 28 atoms in our body. Also, during the COVID pandemic, material science and engineering played actually a very crucial role, as you might remember, in fighting that pandemic. So, we used the Defense Production Act to produce many critical materials and components, like with masks and things like that. But even the vaccine itself, the mRNA vaccines, those basically needed to be protected to be able to go into the cells. So basically, those mRNA vaccine here had to be coated with something like lipid nanoparticles to make sure that basically they will not be destroyed by any uh, acids in the body or in the cell. So for that reason, we used basically the advanced nanotechnology to be able to basically coat those mRNA vaccines in lipid nanoparticles. And also, you were able to, or another important application during the pandemic was to basically make those um, vials for the vaccine, especially the first vaccine, the Pfizer-based vaccine, basically was meant to be um, saved at very low temperature. So basically, the regular pharmaceutical vials were not going to be basically strong enough to withstand this temperature. And basically, we had to use basically a relatively new type of glass that was basically at that time made by Corning, which is of course a very famous company that make glass display for many smartphone and other applications. So there is basically at that time it was predicted the normal or regular borosilicate based glass would not be strong enough to serve at those low temperature, and it was a luckily at that time or a few years before the pandemic that basically Corning came up with even more advanced glass that will basically prevent cracking and fracture at lower temperature, which basically had a little bit of um, composition change from the normal or the regular borosilicate glass. It had a little bit lower concentration of boron in that glass, and that show it to basically show or show it to have a higher fracture resistance. And because of the fact that engineering and medicine are basically uh, connected and basically can work there, or there are several synergetic ways of looking at applications in both disciplines, and the materials that we as we just talked make an interesting linking between those two scientific disciplines. In many college and universities around the nation and here at Texas A&M, there has been basically new kind of hybrid degrees and colleges where you can basically get an MD and a Master's of Engineering degree at the same time. So you can also basically get such hybrid degrees, and that's again to is a nod or basically to the fact that we do need really to be able to kind of have different or have interdisciplinary measures and try to connect what would initially seem like two different fields in order to improve and accelerate the progress in those fields together or at the same base in a sense. So basically, again, kind of to summarize why it's important for all engineers to understand the materials is again to basically be able to make any devices or components. We have to design them based on the best available materials, and to select those best materials, we have to have knowledge of the behavior of materials and prediction of how they will serve under the operating conditions. And that will happen by, or we can achieve that by looking at the structure property relationships. So once we establish those relationships, we can use them to guide us in this process. And this is specifically true for nuclear materials because, as we mentioned, nuclear materials have unique requirements, whether during the licensing of reactors or basically in just handling of nuclear materials on daily basis that requires special attention and they have special properties. Also, nuclear materials require very high standards because of that. And also, in many cases, we want them to serve for longer times. And of course, for nuclear energy systems and applications, most of the activities would be basically regulated and must follow standards and must follow basically um, uh, the handling and transport instructions related to that. So again, this is just to remind you with the most important concept of this field or in this field, which is basically we have four pillars to be able to perfect or optimize the performance of any uh, engineering component or device, and that's basically the processing structure, properties, and performance. We establish relationships between them, and by doing that, we can basically look at it in the reverse direction, and we can ask the question how to improve or optimize the performance and go back and start from the processing and structure and properties to be able to select the best material and the best manufacturing method to improve the performance of a specific application. So it is this fact that we have four pillars, and it's the connection between those four pillars that give us or guide us into uh, optimizing and selecting the best material. So the selection process for engineers would be that we have application in mind and that will basically require specific properties. So we might need to improve the thermomechanical properties or the magnetic properties or the electrical properties. And for that, we have to look at basically specific structure and composition that would optimize those properties. And based on that, that means to arrive at that structure and composition, we will have to use specific, basically, manufacturing method or processing method to be able to achieve such specific composition and microstructure. So, of course, there are different ways to classify materials. So the traditional and most popular approach would be based on the type of bonding. That's something that we are familiar with, which is basically we can classify materials or categorize materials into metals and their alloys, ceramics, and polymers, and hybrids or composites. So composites or hybrids is that's when we are basically combining together two or more of those family of materials, and that's usually to try to get the best of the two worlds. And this traditional classification is still in use because it makes this connection clear between the structure and properties because the different types of bonding in those materials will lead to basically similarity in the physical properties within the same family and basically uh, some changes or deviation from one family to another. So basically that makes it relatively easier when we try to select material based on a specific property. However, now, of course, with the advancement of manufacturing and the large number of materials that are available, we can also think about other kind of classification. So we can talk about, of course, very specific types of materials like nuclear materials, electronic materials, magnetic materials, optical materials, because each subfield of those basically functional materials has been growing and expanding a lot over the last few decades. And of course, we can talk about biomaterials. And now, of course, with the advancement in the way we manufacture the materials, we can also manipulate the materials at much smaller scales. We can make nanomaterials and so on and so forth. So again, we went over that already. So basically, based this traditional approach of classification is still very popular because it categorizes really the different materials and associate them with to different families based on the bonding, which is usually affect their properties. So members of the same family will have similar, relatively similar physical properties. And then we can even zoom in and uh, try to classify things more precisely. So that's also related to several of existing databases. So basically, when we look at data sheets and databases, we can see that basically there are even uh, more and more uh, precise description of materials. So even within the metals and alloys, we can be talking about aluminum alloys, titanium alloys, steels, nickel-based alloys, and in each of those alloys, you will find different series and series numbers. Those usually have relatively different compositions. As we mentioned before, an alloy could basically be consisting of 10 or more elements. And then each of those series will have different properties and data sheet. In many cases, each of those series are optimized for a specific environment and or a specific range of temperatures. So when we talk about ceramics, so if we look at those different families of materials, we can see the reason why this is a traditional and popular classification is within the same family of materials, we have more or less consistent properties, common properties. So ceramics will have high melting point, they will have high stiffness. However, they are usually not good conductors of electricity or heat. Also, they are very brittle, meaning it's usually relatively easier to break them, or they are not fracture resistant. And glass could be also kind of a relatively having some properties that's similar to ceramics, but not all of it. A lot of glasses are amorphous as opposed to ceramics being um, crystalline, but they share some properties like basically insulating in terms of electricity and heat. Also, they are, of course, much brittle, more brittle than other ceramics. If we look at polymers, so mainly those are attractive because of their low weight and low stiffness. And if it's a, even at the very top of this scale is basically what we call elastomers, which will have even a much lower stiffness. And then metals are basically kind of the opposite to ceramics in the sense that those are ductile. They will give you a warning before fracture so they can accommodate a lot of plastic deformation. I'm going to talk about the reason behind that. And they are usually also stiff. However, and of course, they are much more conductive as a material compared to ceramics and polymers because of the excess, electrons and the way the metallic bonding uh, behave or induce this freedom in those electrons to move around. However, usually with the exception of refractory metals and their alloys, usually their melting point is not as high as ceramics. Then we can think of the composites or hybrids, which could have properties or could be optimized to have properties of both or of two or more classes of materials to try to get the best of many worlds. However, because of that, they are usually more difficult to make, and that also translate to being more expensive than traditional or non-composite materials in general. Also, we can think about classification or classifying the manufacturing processes in a way similar to classifying the materials. So this is just to discuss that from a big picture point of view. So we're not going to talk in details about the manufacturing methods here in this course, but mainly we can think about a families of processes in terms of basically the primary shaping and then secondary shaping and then joining, especially for large equipment, and then surface treatment and especially for materials serving in harsh environments. So we start with raw materials and then we do some kind of primary shaping is basically to shape it in the desired form, and then we can use machining and heat treatment to either make this shape more precise or to change some of the properties with heat treatment. Then we can use joining to basically make larger components, and we can use surface treatment to add some protective layers at the surface to uh, make it last longer or make it more compatible with uh, challenging environment. So for primary shaping, we can use something as simple as rolling and forging, where basically we are plastically deforming the piece of material into the desired shape. That usually work for ductile materials like metals and their alloys. We can use some kind of casting, so basically solidification, whether it's sand casting or injection molding, depending on whether we are dealing with metals or polymers. We can also use, there are other laser-based techniques that are more advanced with something like ceramics. We can use sintering and sintering methods. So depending on the type of material and basically whether they can uh, melt at relatively reasonable temperature or whether they can deform under mechanical deformation, that will guide us toward basically which manufacturing method would be more suitable. And also, if we have a desired shape and microstructure, that could also be another factor in deciding which manufacturing method would be more appropriate. Then we can use to our advantages machining and heat treatment as a secondary process to finalize the shape and to also relatively change the properties. So with heat treatment, as we will discuss in detail later, you can basically change some of the thermomechanical properties of materials. Then we can use joining to basically make a larger equipment or tools. This could be something as easy as fastening and riveting, or we can use welding and adhesives. So those are different options that we have while basically trying to put the material or the piece of material into final shape. And then eventually, in many cases, we also would like to apply some kind of surface treatment, whether just for the polishing of the surface, or in many cases, if the material will be used in corrosive or oxidizing environment, then it would make a lot of sense to add basically protective layers. Sometimes even we try to add just some compression at the surface to minimize surface fracture. And we're gonna discuss basically the details and advantages of that when we talk about the structure properties of material or the mechanical properties of structural materials. Then also, if we look at some of the available databases, then we can also see that, or we can rank and classify those manufacturing process in a similar way, and that give basically guide for the engineers to pick and choose what would be the best path to basically follow in order to reach the best specification of your basically piece of material or equipment. So if we already know what properties we need to optimize, then we can, and what type of material, we can basically down select what type of material, and then we can also down select what type of processing methods that we need to use. Then, of course, an important advancement in that field of manufacturing of materials is basically what we call additive manufacturing or 3D printing. And that's, of course, considered as the next really industrial revolution. Has been going on now for a couple of decades, and it is improving year over year. 3D printing, of course, it gives us a lot of freedom and flexibility in designing the structure of the material and designing that structure at different scales, right? So this is basically, there are different uh, types of additive manufacturing and 3D printing, but basically one relatively straightforward example to think of is basically using um, for the case of printing metals, where basically we are using a powder and laser to melt those powder layer by layer, and then we basically deposit this layer by layer until we have a specific 3D structure that we can use CAD or AutoCAD to basically design it. So we can see that this could be handy in many applications, especially in basically isolated spaces or environment. If we need to basically use a tool that we don't have, or that basically a tool has failed and we need to replace it, then we can basically use 3D printing to basically print those tools. And here at Texas A&M and in many universities around the world, there are many basically labs that are dedicated to additive manufacturing and 3D printing, whether for research or for education. So here we have basically the material characterization facility and the Aggie Fab, where basically we use advanced 3D printing and characterization methods to look at the structure also of those printed components. So we can then talk about basically something that's important in this down selection process is basically what do we have at our disposal in order to accelerate this process of selecting materials. So as engineers, what do we use to basically guide us in this selection process? So we can start with a very traditional textbook approach where basically look at the bar chart and bubble chart of materials. So that's when we are trying to optimize just one or two properties of materials. So for the bar chart, for example, that's basically you are trying to optimize just one property. So in this case, this is the modulus or the stiffness of the material. So you can see that basically there are large difference and large deviation or large range of the order of magnitude of the stiffness of materials, and that's of course easy to see or understand when we look at different family of materials. So we know polymers and plastic would be very elastic, have very low stiffness, and then metals and ceramics would have basically the highest values of those stiffness. Then we can look also at trying to optimize two different properties at the same time. You can see that could be important for several applications. One clear example is with aerospace. We're always trying to find light materials in addition to optimizing other thermomechanical properties of those materials. So if we are trying to look at the combination of the stiffness and density, we can see again that while metals and their alloys and technical ceramics have high stiffness, you can see that also they are heavy. So they might not be the optimum choice for some aerospace-based applications. However, there is usually a trade-off. There is now a lot of composites, especially carbon fiber-based composites, that could basically give you a good trade-off between weight and stiffness. Of course, we can look at more advanced databases, whether those are basically paid by or have membership to get the details of the data sheets of materials, or those are open source. And there is recently a lot of research and motivation to increase basically the accessibility to those databases to improve the material science research in general, and basically to accelerate the process, of course, of exploring new materials. So in general, as we mentioned at the very beginning, we have huge number of engineering materials. So we definitely need a more detailed databases and access to those. So we don't just, of course, utilize on those traditional or classical bubble chart and bar chart. And again, this is just a reminder that this number is really related to engineering materials, but if we count basically all synthesized materials, that number would be much higher. The good news, however, is now this is a very growing field. So basically, this is now what we call materials informatics, which is basically to come up with all those open source databases to try to accelerate the process of exploring, deploying, and selecting materials. So many of those open source databases will have materials that have been synthesized with, and their properties and structure were actually measured experimentally, but also they have a lot of materials and structures that are predicted based on modeling and simulation, mainly basically DFT and first what we call first principle predictions and models. So this helps the community to try to basically look for what would probably be the best options and candidates of materials. Of course, that process would be accelerated, and it has already been accelerated using uh, current and advanced tools like AI and machine learning and deep learning. And this is definitely expected to uh, be even more efficient and grow more in the very near future. So we can think of now as basically in kind of autonomous laboratory and to some extent automatic discovery and exploration of materials. This is still the efficiency of that is still not very high, but it's definitely very promising and will definitely change or evolve this field dramatically in the next few years. So one thing also to keep in mind when we talk about materials is inherent multi-scale nature of it. That's what we talked about at the very beginning when we talked about the different scales. So if we look at the different features that we can see in materials and at different scales, so of course on the atomic scale, we will see basically depending on the family of materials, we'll see the organization of atoms in different ways. But at what we call the micron scale, that's where basically you see these microstructure features like grains and grain boundaries and interfaces. And we're gonna discuss those in details as we go on in this course. So this, we can still not see it by the naked eye, but we can see it under the microscope. And those are basically features, as we will discuss later, is basically what limit and the performance of the material because it does directly impact their physical properties, right? And we're gonna discuss that as part of the fundamentals of how we do establish this connection between structure and property. And those features, interestingly, would be different, of course, from material to material, and that's why materials have different properties. And that would be the case for different classes of materials. So ceramics, for example, would have, even on the atomic structure, would look different than metals because of the fact that we have different ions, and that will lead to specific configuration and distribution of the atoms. And then on the grain and the micro scale structure could also look different depending on how we make this material. And the cracking mechanism, of course, is different because ceramics are much more brittle. But the point is, we usually at this micro scale, that basically what govern the thermomechanical and in general physical properties of materials. Same with polymers, also will look different on different scales because the different type of bonding and the chains of molecules and the van der Waals bonding across across the chains. And of course, hybrids and composite will depend on which types and classes of materials you are mixing and how you are making them. So the microstructure is very important. So, and we're gonna discuss that in detail later also. So basically how you make those composites, how you manufacture them with a specific microstructure and how this specific microstructure affect their average properties at the end. So it is again very important to see this connection between the material type and class, which is mainly governed by the type of the bond, and the microstructure and the physical properties. So this is really the main focus of this field, is to connect those three aspects or three pillars of material science. And we can, again, going back to the traditional way of classifying the materials, we can clearly see that this is indeed observed. So basically, metals, if we talk about density, because metals have metallic bonding, we can pack them very well, so they have very high density. Ceramics, uh, relatively well packed, although not as well packed as metals because of the interaction between positive and negative ions and the different types of bonding. Polymers, of course, those are very lightweight material from lightweight elements, and composites usually depends on how you make them. So we can see this connection between bonding and properties. It's also the same if we look at the stiffness. So again, metals and ceramics will rank high because of the high bonding energy, and polymers will rank lower because basically there is only covalent bonding within the chain, but there is only van der Waals or weak bonding across the chains of molecules. Composites would be usually in between depending on the components of those composites. And those electrical properties, we have all the same, again, because of the bonding. Metals are very conductive because of the delocalization of electrons and how free they can move around in the metallic crystals, while polymers and ceramics are basically insulating. However, we have this very important material in between here, the semiconductors, which are basically the materials behind all of our portable electronics, and that's because we can easily change the conductivity of those materials by basically doping those semiconductors to increase the number of electrons or holes, which are the carriers of electricity. Then one clear example where we can relate the microstructure and the processing and microstructure and properties is with the steels. So steels are very versatile material. We use them in many applications, and that's because we can relatively change these properties. So one important mechanical properties that we're going to talk about in detail later, it's called the hardness. It's basically the ability of a material to resist surface scratches. So if the material basically is highly resistant to that, it will have high hardness number. So something like diamond is the hardest material. It will have large number. It can scratch any other material, but it's much more difficult to be scratched. So steels based on the microstructure, something that we're gonna discuss later, whether we have martensitic or austenitic or ferritic steels. Those are different crystal structures of basically iron carbon based alloys. So it turned out that we can actually control those hard phases. So the martensitic phase, which is a hard phase, has a high hardness number. We can basically control its microstructure and basically control the fraction also of this phase by controlling the cooling rate. So by controlling the cooling rate, while we have the same composition of steel, we can have different microstructures. So this is one way of utilizing a manufacturing method to induce specific microstructure and obtain specific improvement or enhancement of a particular property. In this case, it's the mechanical properties, hardness number of this alloy. Other transport properties that we can also utilize the structure or utilize the composition in this scenario to change its properties is basically something like the electrical conductivity. Here it's showing the resistivity, which is basically the inverse of the conductivity. So if we have a pure crystal of copper, the resistivity is very low, meaning the conductivity is very high. However, if we start adding some nickel to copper, it basically increases the resistivity, meaning it becomes less conductive. And that's because when we add nickel to copper, the atoms have relatively different sizes. So there would be basically lattice strain, and we are basically producing Boyne defects. We're going to talk about Boyne defects and describe them in detail later. So those are basically interacting with carriers that are transporting electricity here, like electrons in this example. So basically, those defects and lattice strain will scatter the electrons, the carriers of electricity, and therefore they will lower the conductivity of the material. Same with the thermal conductivity. So if we add zinc to copper, you can see also the thermal conductivity is decreasing as we increase the composition of zinc. Sometimes, of course, we want to increase or decrease the thermal conductivity. So in space shuttle applications, of course, like with the re-entry to the atmosphere, there will be a lot of heat, and we want to have some protective layers that basically would be almost insulating, so basically have very low thermal conductivity. So we use something like silica fiber insulation. So those are basically porous materials, and any and most porous materials would have a very low thermal conductivity, and therefore they will not conduct heat very well. And by doing that, we can basically protect the underlying equipment and systems. Then even actually something like optical materials, you can see our optical properties of materials, you can see that those will also be controlled by the underlying structure of the material. So we can use this, or we can talk about the same material. So for aluminum oxide, we can see that if we make them as a single crystal, they don't have any microstructure feature. It's just one single crystal. There is no grain boundaries or interfaces. Then basically those become very transparent because now light or photons can basically um, uh, go inside the material without scattering. So can basically uh, they can they are not interacting with any microstructure feature, and therefore the material become transparent. However, if those photons have energies or have wavelengths that is on the same size of any kind of underlying microstructure features like grains, for example, or porosity, then they will interact with those, and there will be they will be scattered, and therefore basically the material will become less and less transparent. So if we have just grains, we can see the material is almost semi-transparent. But if we have also porosity, that means there are many microstructure features, grain boundaries and grains and pores and their interfaces, and that basically give much higher probability of scattering of those photons, and the material become basically opaque. So this is again, it's the same material, same composition. We didn't change anything. except the microstructure. So it is this underlying microstructure that we cannot see by the naked eye, but we can see under the microscope, and we can use different manufacturing methods to induce those different microstructures. We can use that to change the properties of material even without changing the material itself or the composition of the material. And again, that speaks to this important relationship between the underlying structure or microstructure and the properties of the material. So this is why this link between structure and property is one of the most important connections that we need to make as materials engineer, and one of the main goals of material science and engineering to connect those two pillars out of the four pillars of material science and engineering. But eventually, the ultimate goal is to connect the four pillars and use that in either making new materials, optimizing existing materials, or selecting the material. So again, to sum up basically what we discussed in this very introductory lecture today is basically we are as nuclear as or as engineers in general, of course, nuclear engineers in particular, we are always looking into trying to choose or select the best available material for the application in mind. And to be able to do that efficiently, we have to be able to understand the relationship between the performance, properties, structure, and processing. So the four pillars of material science and engineering. And once we understand that, then we can use that in selecting the material, but also we can use that in exploring new designs and new applications. So this is important for both scenarios, whether selecting the material or whether imagining basically a new application of novel materials. All right, so this is basically a kind of generic introduction to the field and to the importance of materials in different disciplines and majors, and how engineers, regardless of their major, need to understand some of those fundamentals, and also to kind of summarize what is really the most important concept and essential fundamentals of this field, which those are the four pillars that we talked about, and how we connect them and use that to our advantage. So the next lecture, which would be also introductory lecture, this would be more of focusing or geared towards basically the nuclear energy system and nuclear energy applications, and what we need to worry about and consider in selecting or optimizing materials for nuclear energy applications. So of course, we need to think about the nuclear properties of materials. So that's basically the only engineers who would consider or think about nuclear properties of materials would be nuclear engineers. And also, of course, we need to think about what would be the radiation effects on materials and how we account for that and take that into account while basically selecting the materials. So we will discuss the basics and fundamentals of that during our next lecture. Right. All right, thank you very much. And if you have questions, please, basically, you can comment on this lecture or you can email me directly. Thank you.